Hello everyone, and welcome back. Now, with single variable optimization, we introduced Newton's method of a way of finding those critical points to the function that you want to optimize. Now, this is an excellent and quick computational method that can really expedite the process of complicated problem solving. What the purpose of this lecture is to do is to extend that method of Newton and bring it up into the multidimensional context. Now, as we saw a few videos ago, a lot of the point of these multidimensional or multivariable optimization problems is to solve the gradient equal to 0. So it's a similar kind of root finding problem. Therefore, we would like to have a similar method to Newton's method that can help us to identify those roots. Let's start with the general idea. The general idea is that I have a system of functions. So imagine I've got these multivariable functions that I would like to solve equal to 0. So I have n spatial dimensions, and I'm going to assume that I have exactly as many functions as I have variables to solve here, okay? So in the context of an optimization problem, this is going to represent the gradient of a function. But for now, let's do this completely abstractly, okay? So we have variables x1, x2, x3, all the way up to xn, and we have functions f1, f2, all the way up to fn, which we would like to solve all of them equal to 0. Okay, so how is it that we are going to do this? Well, really, the principle is exactly the same as it is in finite dimensions, or in one dimension, sorry. And it just comes from taking a Taylor approximation. So if we have a good initial guess at what our root should be, so let's call it x0 with a vector notation over top of it. So this is what I am guessing my root should be for these functions, okay? So the vector notation is telling you this is n components of a vector. Okay, then what I could do is I could expand my function f1 near x0 using a Taylor expansion. So this would be f1 of x0 plus, now we have partial derivatives. It's going to be a little bit uglier, but this is going to be the partial derivative of f1 against the partial derivative of x1. And then we've got x minus x naught plus the partial derivative of f1 with respect to x2, and then x minus x naught. And you keep going and you keep going until you get all the way up to the last variable. So xn, x minus x naught. Okay, so the vector notation really here is the only thing that makes this ugly. And what I would like to do is I'd like to do an approximation by just a linear Taylor expansion. Okay, so I'm not even going to go to higher order terms here. This is just a equation of a plane. And then what I can do is I can do the same thing for every single one of these functions. I can do this all the way down to f of xn, which would be approximated by fn, pardon me, of my guess, plus the partial derivative of that last function, x1, x minus x naught. Sorry, there should be arrows above this. And then you can do the second partial derivative. I'm not going to write it just because it's so much writing. It's more writing than it is thinking. And the last piece here is xn, x hat minus x vector. Okay, so what I can try and do is I can actually absorb all of this into one huge matrix. Okay, so again, this is a linear equation. And so what this really tells me is that I have this, f1 of x f2 of x all the way down fn of x is equal to, okay, so now this is at the initial guess, all the way down fn of x naught. So I'm just using vector notation to clean it up. So it's all of this. And this is, I guess I should put approximately equal just so everything is consistent. Approximately equal, then all of the initial guesses. Then, now let's turn this into a matrix, OK? And here's how I want to write this thing. In the first component, I have the partial derivative of f1 with respect to x1. And this is evaluated at the initial guess. The next is f1 with respect to x2. Again, at the initial guess. And then all the way out until we get to this last partial derivative. Again, at the initial guess. That's the entire first row. The entire first row, you'll notice, is the gradient of f1. Same thing, the entire second row is the gradient of f2. And you can keep going down until the last row is the gradient of fn. So in this case, it's just an exercise really in subscripts. It becomes very burdensome to write this, but I don't think it becomes very burdensome to really think about it too hard. Right? It's just an annoying thing to write down more than it is an annoying thing to think about. And this is a vector, and then it's multiplied by x minus x naught. Now, this matrix right here is a very special kind of matrix. This is called the Jacobian matrix. Typically, it's denoted by a big capital J. But now what you can see is that I can invert this. If this is a matrix, if this matrix is invertible, then I can solve for x in this case. And so let me do it up in the corner here. What this would give me is that my better root, given in terms of my old root, follows this form. So in this case, I get minus. I'm going to use J for Jacobian of x0. So that denotes this whole matrix here evaluated at x naught or x0. And it's inverted because I needed to get it away from my x right here. And it is inverted against this whole vector of initial guesses, right? So again, I want to solve this piece equal to 0. So I set all of this to 0. I pull this over. I invert this. And I pull the x naught over to the left-hand side or the right-hand side, whichever way you want to arrange this. But in this case, I get f1 of x naught all the way down to fn of x naught. That gives me the Newton update on my root. So it takes a guess that I had, it refines that guess, and gives me a better estimate of the root. Now you can bootstrap this process, right? So once Newton gives you a better update, you can use that as your old guess and use Newton to update it again, just like what we did with single variable optimization. I want you to recognize that this is very similar. I mean, it really is the same process as single variable. The only difference is I can't really divide vectors anymore. So in this case, I have matrix inversion instead of dividing, right? So what you should really do here is go back and look at single variable Newton's method and compare it to the Newton's method that I just gave you right here. Make sure you can see the correspondence between the vector notation and the single variable notation and see that it's exactly the same process. All it is a Taylor expansion and solving that Taylor expansion equal to 0. Now, of course, there's technical caveats here. First of all, we actually need this thing to be invertible. So that's a piece that we need to be careful of. The other piece of it is we need a good initial guess. So with single variable problems, I've said that you can get a good initial guess just by maybe looking at the graph. In the case of multivariable problems, that could be very, very difficult, right? We can't graph things in more than 2 dimensions. So the question is, what could we do? Well, unfortunately, there is no real prescription for this, right? Finding good initial guesses is an art. It is a very difficult thing that most people kind of just do through random searches. So what you could do is you could test a bunch of random points in your domain and see which one of them comes closest to being a root. Then what you could do is you could use that as your initial guess and let Newton help you out. Right? So it's a 2-step process. Finding that initial guess is just as critical as applying Newton's method, because Newton's method is only as good as the initial guess that you give it. All right, let's see Newton's method in action for an optimization problem. Okay, so the example that I want to do is I want to imagine that I am a manufacturer of lawn furniture. I'm making 2 different kinds of lawn chairs, okay? One with a wood frame and another with an aluminum frame, okay? And here, let me put things together for you, and let's take a look at what the equation will look like, okay? So in this case, I'm going to let Z be the profit function that I would like to optimize. I want to find the maximum of this function. And let's assume that X is the number of wood frame lawn chairs that I am producing, okay? So number of chairs being produced, and imagine this function is given to you. It tells you how much the maximal price per chair is that you can offer depending on how many of each of the wood frame and the aluminum frame that are given to you. Okay, so this is going to be really manufactured to be a complicated example, primarily for the purposes of applying Newton's method. Okay, so then the number of wood frame lawn chairs against the price per lawn chair. So let's imagine it's 10 as a sort of base price plus 31x to the power of minus 0.5 plus 1.3y to the power of minus 0.2. Okay, so it's a complicated function. X is the number of wood frame, Y is the number of aluminum frame lawn chairs that you're producing here. Essentially what this is saying is that if you're producing a lot of these lawn chairs, then you're making enough money that you can bring the price down to $10, right? Because if X goes to infinity and Y goes to infinity, these things disappear. So what this gives you is the intermediary transition to producing a lot. And this is the price per lawn chair against the number of lawn chairs. And then let's imagine it costs us $18 to produce each wooden lawn chair. Then we can do the same thing. We have the aluminum lawn chairs, the number that you produce, and they have another sort of ugly looking complicated price function. So 5 plus 15, in this case, y to the minus 0.4, again, disappears as y goes to infinity, plus 0.8x to the power of minus 0.08, so very, very small. And then it costs us $10 base to produce each lawn chair. Okay? Now the question is, optimize this, right? I would like to find the global maximum, so what is the production over all possible numbers, x and y, to determine how I can maximize my profit, right? So clearly, this is subject to x and y being greater than or equal to 0. But that's it, right? So we don't need to use any Lagrange multipliers here. It's a really, really simple problem, aside from an ugly function, where we're just optimizing in the first quadrant of the Euclidean plane. Okay, well, the first thing that we're going to do is we're going to compute the gradient, right? Because we've seen that if we want to optimize this thing, we just need to set the gradient equal to 0. And that will give us the maximal or minimal value, the critical points inside of the domain. Okay, let's compute some gradients. So in this case, I have the partial of the profit function z with respect to x. So these things are not going to be particularly fun to compute, but you can do it. I believe in you. This is 15.5 x to the minus 0.5 minus 8, and then plus 1.3 y to the minus 0.2, and then minus 0.064 x to the power of minus 1.08. Okay, so not the prettiest function I've ever looked at, but that's okay. Same thing here. I can compute the gradient with respect to y. Again, it's going to be ugly, but if you can stand to look at it, it's not that bad. Minus 5 here, and then plus 0.8 x to the minus 0.08, and then minus 0.26 x times y to the minus 1.2. Okay, so now what I would like to do, the goal, solve the gradient of z with respect to x equal to the gradient of z with respect to y equal to 0. That's the whole point, right? That is the gradient function. These are partial derivatives. That's both partial derivatives. That is finding that critical point inside the domain. Now, again, there's a bit of a problem, right? Because if I'm going to apply Newton's method here, I need to figure out, where I should be looking. So the first thing that I can do is I can throw this into a function plotter. So this is only a two-dimensional function. This is something that can still be plotted in 3 dimensions. 2 space dimensions, x and y, and 1 output dimension, z. Okay? So you could use, say, Wolfram Alpha here, or you could use Desmos, or a number of online platforms that are free and accessible to plotting these things. You just need to put this in, and what you can do is you can take a look at this thing, and you can say, where does it look like the maximum is? Okay, so for me, when I did this, I formulated the following guess. I said somewhere around the point 5, 6. It looks like the solution to this thing is around x equal to 5 and y equal to 6. Okay, so that's not exact. That is certainly not the exact maximum of this thing. But, from my eyeball test, it looks like a good enough guess to get Newton started. Okay, so essentially, I'm going to apply Newton here. So apply Newton. And the way that I'm going to apply Newton's method is I'm going to use the first function. So I'm going to say f1 of xy. This is equal to the gradient of z with respect to x. Remember, it's the gradient that I want to set equal to 0. So that's the first function. And the second one is the gradient of z with respect to y. 2 functions, 2 unknowns. That's good. That checks off everything for applying Newton's method. And the next thing that I'm going to need is that Jacobian matrix, J of x comma y. Remember, this is that big matrix of partial derivatives. The first entry of this thing is the partial derivative of f1 with respect to x. Okay? So here's my f1 function. I need to take another derivative with respect to x. So it's going to be a second derivative computation technically. So again, bit of a pain, but you can do it, right? It's just derivatives. So in this case, 0.06912, and then y times x to the minus 2.08 minus 7.75 x to the minus 1.5. So you should do these yourself and make sure you're getting the same numbers. And then minus 0.064 x to the minus 1.08 minus 0.26 y to the minus 1.2. Okay, so that is here. These two terms are the partial derivative of f1 with respect to x first, then the partial derivative of f1 with respect to y. Okay, so that's the gradient of f1 in the first row. Then in the second row, negative 0.064 x to the minus 1.08 minus 0.26 y to the minus 1.2. Okay, so it's a symmetric matrix. Actually, that's quite interesting to me. And now the partial derivative of f2 with respect to y, that's all that's missing here. I get 0.312 x y to the minus 2.2, and then minus 3.6 y to the minus 1.4. So it's not pretty. I don't love looking at it, but that's okay, right? It's just a number. Now, one thing that you might want to remember if you're going to do this, all right, so clearly this is going to take a lot more steps than just doing Newton's method was with single variable optimization, right? At some point, you're going to have to invert a matrix. Now, you are more than welcome to do this on the computer. In fact, you're encouraged to do this on the computer. This is a quick little for loop. You can use, say, MATLAB or Python. All of these things have built-in matrix inversion computers, so you don't have to do this by hand. But if you want to do it by hand, well, it might be good to remember the inverse of a 2 by 2 matrix, right? This is 1 over the determinant of that matrix. Then you swap D and A, and you negate B and C. So remember, Newton's method requires me to take an inverse of my Jacobian. All right, so Newton says, okay, so my new guess, x and y, is given by my old guess, x0, y0, minus the Jacobian at x0, y0, inverted, and then times f1 of x naught, y naught, f2 of x naught, y naught. Okay, so it's going to be a lot of work, right? Especially if you don't use a computer to help you with this. So here's what I did. I took my initial guess, 5, 6. I put it into this big old formula, and I got a new guess. Okay? So it takes a lot of computation step to step. It's a huge pain. But then when I got a new guess, I put that guess back into Newton, and I got a better guess. Okay? And so what I did is I iterated this 10 times. And what Newton gave me, so after 10 iterations, right? And this cost me maybe less than a minute of my time to program this up. All right, sorry, to run this as a program on the computer. Again, you can do it by hand. It might take you way more time. But if you just do a simple little for loop, it took me less than a minute to run this. I got a guess at the solution, which is 4.68959 and 5.85199. So that's what Newton gives me. And at this point, it gives me a profit of $52 and 0727. Okay, so 520727. So clearly I've sort of scaled the numbers, right? If I'm a company making lawn chairs, $52 in profit is not great for me. You can imagine this being in thousands or millions of dollars. It's up to you how you want to sort of think about these things. But that's the point, right? Now I've got myself the optimum value inside of this feasible region. Now I can hand the problem back over to my pencil and paper, and I can figure out if this is a maximum or a minimum inside of the domain. And then what I can do is I can also check along the boundaries. Remember, we need, with these multidimensional, these multivariable problems, you need to check when x is equal to 0. That will nullify this entire first term and give you just a function of y that you need to optimize. And then you can check when y is equal to 0, which nullifies this entire second term, give you just a function of x which you need to optimize. You compare the 3 optimum values that you just got over those respective optimization problems. And in fact, you will find that the maximal profit you can get here is this one that you found with Newton iteration. So the way that you should think about this is Newton iteration is a way of helping you update your guesses. And you can be done in a computational manner, but it can even just be done by, you formulate a guess and just make it better, right? Step to step, it might take a little bit of work, but this can be used to complement your optimization problem solving, right? It doesn't give you everything. It just tells you where the location of these points are, where the gradient is equal to 0. You still need to do lots of work. You're not handing this off to a computer. You're not handing it off to an algorithm. You're just letting that algorithm walk you through and help you get better approximations of your root. What you do with that is entirely up to you. Okay, I'll see you in the next video.